Have you ever heard a sound that wasn't actually there? It's not as weird as it sounds. Today we're diving into a really cool auditory illusion, kind of like a magic trick for your ears, where we're going to figure out when a sound is not a sound at all.
You know that sound, right? When two guitar strings are almost in tune but not quite, you get that pulsing wah, wah, wah effect? Well, here's the big question. Is that wobble a real physical sound wave being created in the air? Or is it just a ghost, an illusion our brain is creating?
All right, so let's start with this thing we all know, what scientists call acoustic beats. But for us, let's just call it the phantom wobble. So, what's actually going on here? Well, when you have two sound waves that are super close in frequency, they start to interfere with each other. Sometimes their peaks line up and the sound gets louder, and sometimes a peak hits a valley and it gets quieter. This whole up and down in volume is what we hear as a beat. But notice, it's just a change in loudness, not a new sound.
And this is where the real mystery kicks in. As Wayne Garver points out, yeah, we hear these beats all the time, but, and this is the key, just adding two waves together doesn't mean you've actually created a new wave at that beat frequency. This is the exact puzzle we're going to piece together.
So we really need to draw a clear line in the sand between the illusion we're hearing and a physically real brand new sound wave. So let's compare these two ideas, beats versus real waves.
Okay, so on one side, you've got beats. That's the illusion. It's just a volume knob going up and down on the two original waves as they interfere. But on the other side, you have a heterodyne wave. Now this is the real deal. This is a brand new wave at a totally new frequency that's physically born from the two original ones.
So if just mashing two waves together doesn't cut it, then what does? What is that secret ingredient? What's the magic that turns a simple phantom beat into a real, tangible, new heterodyne wave?
To find that secret, we're going to look at a simple experiment. We'll start with what's called a linear test to see what happens when we combine these waves in the most basic way possible.
So here's the setup. We take two waves, both way, way above the range of human hearing. One at 22,000 Hz, the other at 24,000 Hz. Now the difference between them is 2,000 Hz, which is a frequency we definitely can hear. These two waves get mixed and sent through a simple resistor. Now, a resistor is what you'd call a linear device. All that means is it treats every signal the same. It just lets them pass right through.
And when we look at the output, what do we see? Yep, there it is, that classic beat pattern, that wobble. And if you measure it, that wobble is happening exactly 2,000 times a second. That's 2,000 Hertz, the difference between our original waves.
So, looks pretty clear, right? We can see the pattern. It's wobbling at 2,000 Hertz. Case closed? Well, not so fast. Just because we see a pattern doesn't mean a new physical wave was actually made. We have to look deeper.
And here's the big reveal. When we analyze the actual frequencies that are present in that signal, look at its spectrum, the truth comes out. There are only two spikes of energy, one at 22 kHz and one at 24. That's it. The 2 kHz wave, it's nowhere to be found. It's a phantom. The wobble was just an illusion. So, if a linear device, like a resistor, can't do the trick, what can? Well, now we get to uncover the secret, non-linearity.
So they run the exact same experiment again, but with one tiny change. That simple resistor gets swapped out for a diode. Now, a diode is a nonlinear device. Basically, it doesn't treat signals equally. It lets current flow one way, but not the other. It changes things.
And the result? Oh, it's like night and day. A new wave is literally born. A clear, audible 2,000 Hz tone comes blasting out of the speaker. It's not an illusion anymore. It's a real sound you can actually hear. This nonlinearity, that was the magic ingredient.
Now look at the frequency spectrum. We've still got our original waves at 22 and 24 kHz, sure. But look, there it is, a brand new, very real spike right at 2 kHz. The nonlinear diode didn't just let the waves interfere. It actually forced them to combine and create something totally new.
That's right. A real, physical, measurable 2,000 Hz wave that now exists, where just a minute ago, there was nothing. This is a true heterodyne wave. So how in the world does this work? Well, it's all in the math. A linear device just adds the waves together, no big deal. But a nonlinear device, like a diode, it distorts the signal. It's kind of like it squishes it and stretches it. And when you do that mathematically to two combined waves, the math itself spits out brand new frequencies, specifically new waves at the sum and the difference of the original two. Okay, this is all fascinating stuff for a lap.
But what does it have to do with you and me? Let's bring this all back home and talk about the most amazing sound detector on the planet, your own ear.
Think about a few different ways we hear things. A microphone? It's linear. It's designed to be an honest reporter. It only records the sound waves that are actually in the air. A radio receiver? It's nonlinear on purpose. It uses this exact trick to create the audible sounds you hear from invisible radio waves. And then there's the human ear. Turns out, it's a little bit of both.
And here is the big, mind-blowing takeaway. Under certain conditions, especially with really loud sounds, your own ear acts as a non-linear device. The tiny little parts in your inner ear can vibrate in just such a way that they create these new heterodyne frequencies inside your own head. You hear them perfectly clearly, but they don't actually exist out in the air. Your brain isn't just imagining them, your ear is literally manufacturing them.
And that leaves us with a pretty wild final thought, doesn't it? If our perception of something as basic as sound isn't always a perfect recording of reality, if our own bodies can create signals that aren't even there, what other illusions are we all perceiving every single day without ever even realizing it?